We're going to go ahead and wrap up this chapter on charge and forces by talking about like what if we have multiple charges in a situation, how do we find the force, and also what about spherical charges. So just generally what we've done so far as finding the force using our formula K times charge 1, charge 2 divided by the distance between them. What we've done is we've considered all the charges to be point charges, which means like all the charges concentrated into a single point that is infinitely small. The reality is that a charge would tend to spread out somewhat from its location, even if it were on an insulator. So a way to kind of just start to look at that is spherical charges. And what's going to happen is like, let's say we have this metallic ball and it is collected charge on it. So if it has collected charge on it, well, then that charge would tend to spread out all over the surface area of that sphere. And what we can do is I've said, okay, we can look at, spherical charges, but then what we could do is take a look at this charge because the object is a sphere, and we could pretend that it is a point charge like we've been doing all along. But something that we'll be interested in is what is the charge density, meaning how much, as this charge spreads out, how packed up is it on the area. Taking a look, I kind of jumped over this multiple charges idea, is if we have several charges in a situation, I can find the net charge, say, on this one, by finding the net charge between charge 1 and charge 3, and the charge between charge 2 and charge 3, and then adding those up. Now, vectors would apply here, so that would mean that if I was in two-dimensional space, I'd find the x and y components for each force, and then I would add those together, and then I would use trigonometry, inverse tan specifically, in order to go back to just like a magnitude and a direction of the force. So let's go on and let's kind of take a look at this charge density thing. So charge density, we'll have our sigma. I'm not sure why they decided on that symbol, but sigma is going to equal Q, meaning our charge divided by area. And I've specified, since we are talking about a sphere, the surface area of a sphere is 4 pi r squared. So if we knew the radius of the sphere, we could find the surface area if it were not given to us. So we have Q over A is our charge density. And what that's talking about is like how densely packed the charges are on the surface of the sphere. Now, I had drawn a picture of this with a bunch of positive charges, and you should correctly think, well, wouldn't those all repel? And yes, they do. But the thing is that the net between all of these is going to be 0 because they're equally spaced out is the idea, and they're going to repel outward such that the net on the inside here is going to be 0 between them because they will repel from each other. Okay, so 3 charges form a system along the x-axis. Charge A is 9 microcoulombs and is at the origin. So let's go ahead and draw our axis right here. So we have 9 microcoulombs right here. And then we have B is -5 microcoulombs. This is 12 centimeters from the origin. So here is point B, -5 microcoulombs. And then charge C is 4.4 and is 15 centimeters. So maybe like right here, 4.4 microcoulombs. And let's think. Now, our distance here is 12 centimeters for charge B. So that's going to be 0.12 meters. And then charge C is 15 centimeters from the origin. So if this is 15, then this right here would be 0.303. meters between charge B and charge C. So the first question asks, finds the net force on C. So what I'm going to do is first find the force between charge A and charge C, and my net force is going to equal that plus the force between B and C. So let's go ahead and find those individually. So the force between A and C is going to equal K times 4.4 times 10 to the negative 6 times charge A, 9.0 times 10 to the negative 6, all over our distance. So the distance between them is 0.15 squared. So our FAC, now we want to be very careful how we type this in. We do want to make sure we put this in parentheses, and we want to remember that K is going to be 8.99 times 10 to the 9th. Okay, so I'm going to go ahead and type that in and see what we get here. I have K programmed into my calculator, so I don't have to type that every single time that it comes up. So that might be a handy trick for you to do. And make sure we get our exponents correct. And I get the force is 15.8 newtons right there. And so now I'm going to find the force of B on C, and that's going to be K times this time negative 5 microcoulombs. So that's negative 5 times 10 to the negative 6 times 4.4 times 10 to the negative 6. And we're going to have a distance between them of 0.03 squared. So we do expect a large force, or a decent sized force, but because the distance between them is smaller. Let's see here, 5 and 0.03, just typing this in. And wow, much bigger. And K, using this number up here, we get 219.8. Okay, so now we're going to want to be careful here. This one up here, AC, see, these are opposite. These are the same type of charge. They're both positive, so this is going to be a repulsive force. And this right here, between these two, those are opposite, so this is going to be an attractive force. And the trick that I talked about earlier is, even though the formula technically is, if you take a look at the formula for charge, is technically absolute value of the charges, I actually do find it useful on occasion to ignore the absolute value, and in this case that would give us a negative right here. Now, it's not actually a negative Newton force, but it does tell us that it is an attractive because of that. Whenever you get talking about forces of charge, whenever you multiply them and you get a negative, that does tell you that it is an attractive force. So we have a net attractive force. So when I come over here, I actually think it is useful to use that negative, and we would have this 15.8 and minus a 219.8, and we'll get a negative 204. Now, we're not going to want to write that as our answer. We're not going to say that the force is negative 204. That actually really makes no sense. But what we will do is say, all right, here's how we deal with this negative. That is an attractive force. So our net right here is a 204 Newton force that is attractive, okay? Meaning it's attracted to the left towards this negative 5 microcoulombs. Okay, so now the next question asks for the net force on B. So the net force on B is going to be the force of A on B plus the force of B on C. Now, we already found the force of B on C, and that is a negative 219.8. Now, in that case, though, it would be towards the right, towards the 4.4. So there is a little bit of confusion right there, right? And then our AB, we need to find that one. So the force of A on B is going to be K times 9 times 10 to the negative 6 times negative 5 times 10 to the negative 6. All over now. Yeah, I'm going to confuse you a little bit more. This is also an attractive force over here to the left. 0.12 squared. So the negatives, yeah, are not going to help us this time. So you just got to keep straight what is going on in each situation, which direction. The direction does matter. And just typing this in. And I do get negative 28.1 newtons. Now that's an attractive, but we do want to make clear here which way. So this one's being pulled this way with negative 28 newtons, and it is being pulled this way by the negative 219. So those are opposite in direction, right? And actually, now that I'm thinking about that, we may have a mistake up here. So we'll need to take a look. We'll come back up here and take a look, see if I did a stupid mistake with the signs, but we'll get back to that. So we have, so these are going in opposite directions, right? So we would have like one of them add and one of them subtract. Okay, I don't know why my computer just beeped, but whatever. 219.8. So we get a net of 191.7. I'll say that's 192. Now, which way is that going? Well, it's definitely stronger to the right. So I'm going to have 192 newtons attractive, but to the right. Okay. The other one was working against it. Okay, so let's go back up here. So something I didn't consider, and I'll switch color again, that I should have definitely considered is the direction right here for this first part. So the force of BC, I'll write it in yellow. Let's see, BC was attractive, meaning we had it going this way. And then right here, AC was repulsive. So actually, it was going the same way. So actually, we should have added these two together because they were actually acting in the same direction. So we should have said 235.6 newtons. 235.6 newtons attractive to the right. It's being attracted to the charge on the right. All right, let's go on. All right, so a sphere charge has 560 microcoulombs. What is the charge density on the sphere if the radius of the sphere is 3 centimeters? So charge density is our charge divided by our area. I don't know the area of the sphere directly, so I'm going to use 4 pi r squared to give me the area. Now you might wonder why not a box? Could we do a box? Let me talk about that real quick. So suppose we had a box instead of a sphere. Could we just replace this formula with the surface area of a box? And would it work out? And in short, I mean, it would be an okay estimate. It would be okay, but these points are not equidistant, right, from the center as, say, a point right here. So if I had a point on the face, this point on the face is not equidistant from the center as, say, from the point on the corners. So what we'd actually tend to see is that the charge density wouldn't be necessarily equally spread out. It would actually tend towards the corners. And so it wouldn't be evenly spread. It'd just get out to these pointy things. So arcs. So a good example of that is an arc would tend to happen like if you had charge building up at the pointy ends of two, say, exposed wires. You know, it's going to go towards that pointy end and arc across at that point because it builds up at the point. Anyway, so that's why it is important that it is a sphere so that they can equally disperse throughout. So our charge, we're going to do 560 times 10 to the negative 6 all over 4 times 3.14 is good enough. And we'll change this to meters, so 0.03 meters. So what is our charge density? Putting this in. And I get a charge density of 1.49 times 10 to the negative third coulomb per meter squared. Now, you could do it in microcoulombs. So I could have said 560 over 4 times 3.14 times point, or all over this. No, and just did this in microcoulombs instead. And we just need to be aware that the units are different. I think it's generally good practice to keep it in SI units. But anyways, in that case, we'd get 1486, and that would be microcoulombs per meter squared. And we could even just leave it in centimeters, and we could do it per centimeter squared. It's fine, but you need to then label your units. So if you're not using the SI units, definitely, of course, you always should be labeling your units, but definitely if you're not using the SI unit, then you should definitely show what you're doing there. Okay, let's go on. A sphere with a surface area of, so this time we are told the surface area is, so this is our A. It has a charge density of 12.1, so notice the units, microcoulombs per meter squared. The sphere exerts a force, and notice, these agree, right? These units have to agree right here. If one of them, say this was centimeters, if this was centimeters squared, then I would need to change to meters squared. Okay, anyways, so the sphere exerts a force on, that should be newtons, on this particle. What is the distance between the charge and the center of the sphere? Okay, so we have several steps here. In order to find the force between the two charges, we need to know what the two charges are. So we know one of the charges is 1.75 microcoulombs. But we don't know this other charge. We do know its charge density. We want to know the radius, so we do need to find this other thing here. So let's go ahead and find the other thing, the other charge. So our charge density is defined as charge over area. This time we are told the area is 0.0224, and we're told the charge density is 12.1. Now notice it's microcoulombs per meter squared. That's going to be important because we know in the end, when we solve this, our Q is going to be in microcoulombs as opposed to coulombs. So we're going to have to change that to coulombs over here for our force. So now this force, by the way, for this K constant to work, which is the 8.99 times 10 to the 9th, in order for this to be the actual K, then these charges must be in coulombs. They can't be in microcoulombs. They have to be in coulombs. So we're going to multiply both sides here by 0.0224. So we get 12.1 times 0.0224, and that gives me Q is 0.271, and that's in microcoulombs. So when I bring this up here, I'm going to do 0.271 times 10 to the negative 6 to change that to coulombs. So now we are ready to go ahead and type the whole thing in using our constant K. And times 0.271 times 10 to the negative 6 all over our R. We don't know our R, do we? Okay, but we do know our F. So when I multiplied all of this up in our numerator, I get 4.26 times 10 to the negative third. Now I actually have more decimal places here, but I'm going to keep more of them and round at the end. Our radius is what we're looking for. F, we are told from the problem, is this. So how do I solve this? I think we're going to go ahead and cross multiply. So cross multiply, we get 46.9 times 10 to the negative third times r squared equals 4.26 times 10 to the negative third. And then I'm going to divide both sides by 46.9 times 10 to the negative third. And when you do this, you need to make sure that you throw it inside of parentheses so that you don't have a mistake on your calculator. So if you're doing this for class and for notes, I would highly recommend that you actually try on your calculator to make sure that you are typing, getting correct, and getting the same thing I am. So when I divide these, I get 0.09083155565. And that's I kept more places here, and then we're going to square root that. And our rounded answer, so remember we should round at the end, is 0.301 meters. 0.301 meters. I don't think we have another example. Yeah, we don't. So that actually wraps up this chapter. So good luck on your assignment.